Yeah. Well, hey guys, sorry, I appear to be a little bit late getting started. I am so sorry about that. So first thing I wanted to do is talk a little bit about the first exam. It has not been posted quite yet, and that's because I wanted to make sure that everything was as cleaned up as possible before I put that up. I did put up some announcements about it this morning because I'm just about ready to get that posted. So I wanted to walk through, make sure that you guys have read those announcements. It's about making sure that your environment checks are done for taking the test. You need to make sure that you've shown your ID to the camera when you do that. It needs to either be a TTC ID or a state issued ID, like a real ID kind of thing. So make sure that you've done that. That's just so we can verify who you are, all of that good stuff. It's not as much of an issue with some of you because I've met most of you before, but that's something that we need to make sure that we've taken care of. Any violations of the code that's been posted for what you need to do during the test, i.e. your camera needs to be on the whole time, the lights need to be on in the room that you're in, you should be alone in the room that you're in. If somebody walks in, I know that this may happen, just tell them, please leave right now, send me an email immediately afterward. I get it, not everybody respects boundaries. I understand that, it's happened to me. But we need to make sure that there's not any nefarious communication going on, and that may not just be stuff like what I can hear. So I am aware that there is sign language that can be used, whether that be actual sign language or otherwise. We need to make sure that that's not happening. So just to keep things as clear for you as possible, we want to make sure that there's no question about what your intentions are. We try and make sure that that is as maintained as possible. Acceptable forms of calculators, anything that cannot connect to the internet. So I know that TI calculators cannot, some of the HP calculators can. So depending on what your calculator is, you'll need to show that to the screen before you do, when you're doing your environment check. And if I have any questions about it, I'll ask you about it after the first exam. Okay, it probably is not a problem. I just may need to actually see what kind of thing it is. And usually I can go and check one out somewhere and it's not a problem. But if it's something, some of the HP calculators are capable of connecting to the internet and can pull information from it in the same way that a smartphone can. So that's a problem. So things like that would not be acceptable. You cannot use your phone as a calculator. You cannot use a tablet as a calculator. You cannot have another laptop that you're using as a calculator, nothing like that. So you should have one computer that you're using for the exam. Please make sure that that computer is on a desk and not in your lap. Otherwise, it'll cause problems with the Respondus Monitor stuff. And I still need to post some of the things that I've been told from Respondus Monitor about turning some things off before you take that test. Because again, notifications that are being pushed, like if you're because it's more common on the iPhone systems than anything else. But if you get push notifications to your smartphone or to your laptop, that from your phone, that can cause problems with Respondus. So we need to make sure that those get turned off. And there's a list of instructions that I've been given from Respondus that I need to post about that so that you guys don't run into trouble. Okay. So that is an expectation, is that you will have that managed. If you have any problems with it, if that becomes a problem, then we need to talk about that. Okay. So it may boot, Respondus has gotten really attitudinal about it, and it's booting people out of the exams before they're finished if they're getting push notifications. So you will probably notice if that happens to you. You will probably want more time because you will have gotten booted early. So we'll need to talk about how we need to remediate that before you get any additional time. And we'll figure out what we can do about that depending on how long you had to look at the test. Because if you've had time to look at the test, I am reluctant to let you get into the same test again. So, because that's unfair advantage comparative to other people. So we don't want that. So there is that. Are there any questions about the test? Okay. All right. So there will be further announcements about that in case anybody has any further questions, and you can always ask me about that at any time. Like I said, there will be no lecture on Monday, so that you have time to take the test if you have not finished it. Because I have not posted it yet, you're going to get an additional day to work on it, so it'll be due Tuesday at midnight. So, all right. So I'm planning on picking up where we were in the titration lecture, and we were getting ready to talk about stoichiometry and titrations. Now, a lot of this is what we did last term. So this is not new mathematics that we're talking about at the beginning anyway. But I need to remind you guys of all of these calculations so that we make sure that we can get, we're all on the same page about what you should be able to do. So just as we can do calculations for mass or moles of starting material to determine mass or moles of product formed, we use similar calculations using solution concentrations. So if I have 50 milliliters of a 0.05 molar HCl solution that I want to titrate with a 0.07 molar NaOH solution, how much NaOH will I need to add to reach the equivalence point of the titration? And since this is a strong acid, strong base, that equivalence point happens to be at pH 7. So the first thing I need to do is to figure out how many moles of HCl I have present, and then what is the relationship between HCl and NaOH. So since the reaction that I'm looking at is between HCl and NaOH, I will balance that. So HCl, my acid, NaOH, my base, I end up with water and this salt, sodium chloride, based on the fact that we're doing this reaction. Okay. Obviously, these are aqueous components. And this right here is a liquid. So if I were to write a K for this, only these three would appear in that K, the H2O would not. Just a reminder. Since I have 50 milliliters of 0.05 molar HCl, so 50 milliliters, I will convert that to liters. And I have to do that because the molarity is in moles per liter. So if I want to multiply by the volume, I need it to be in liters so that I can multiply by that. I then multiply that by the molarity of that solution, 0.05 moles of HCl per liter. And that will tell me how many moles of HCl I am working with. Okay. So I can pull up my calculator to look at that, because I am terrible with math. So where did my mouse go? So 50 divided by 1,000 times 0.05. Oh, that's not a 5, that's an 8. That gives me 0.0025 moles of HCl. Okay. Because I know that it's a one-to-one relationship between the HCl and the NaOH, that also tells me how many moles of NaOH I would need to be able to do this. That's not what I wanted to do. So I know that this is also equal to 1 mole of HCl, 1 mole of NaOH. That's also equal to the 0.0025 moles of NaOH that are required to reach that equivalence point. Okay. So if I know how many moles I need and I know what the molarity of my solution is, I can take that 0.0025 moles of NaOH and I can divide that by the 0.007 moles of NaOH in 1 liter of NaOH. So dividing by that molarity. And then if I wanted to, I can convert that to milliliters. And that would give me the volume in milliliters that I would need to be able to do this. Okay. So taking that 0.025, dividing that by the 0.007.
Is it because of the M1 V1 equals to M2 V2 formula? Is that where you kind of getting that from? Is that how you're finding the volume?
You just asked me that, and I'm about to smack you for it. No, we can't use M1 V1 equals M2 V2 because this is a titration, not a dilution. M1 V1 equals M2 V2 is only true if I'm doing a dilution. As long as I'm doing a titration, I have to take into account the stoichiometry that exists. M1 V1 equals M2 V2 does not take into account the stoichiometry.
Okay.
So that's why I'm freaking out on you, because you know I've got to think about that. So it would have taken this step right here out. So that it will in theory work because this is a one-to-one relationship, but that is not the way that you should be thinking about it. Because then you forget that you're supposed to take into account the stoichiometry. And what if this was a 2-to-1? Then you'd have the wrong number. But yes, it's that kind of calculation that we're talking about. So we always have to multiply the molarity times the volume to get the number of moles.
Right.
And then from the number of moles of one, I can get to moles of the other. And then for moles of that, I can use the molarity, divide by that molarity to get the volume.
Okay. Cool.
So if I do that, I end up with 357 milliliters that are required to do this. Okay. It seems like a lot. And that's because the stoichiometry or the concentrations are very different. So we have the 0.05 here, molar here, and we have the 0.007 molar there. So because those two things are very different, that gives us a very different number for those. Totally fine. So, and I would report this, I mean, from a technical standpoint, I only have 50 milliliters in my first part. So technically that's only 2 sig figs. So I would typically want to report this as 360 milliliters because that limits how many sig figs I would have in that answer. But again, I try to be better when I write the test so that you'll know exactly how many sig figs I want because this is a little ambiguous. So, okay. So cool with that.
Yeah.
So that's one way we can look at it. Now, another thing that we have done in the past is to take the mass 3.594 grams of acetic acid And I need to know how much I'm going to add from that same ammonia, from a slightly different ammonia complex to react with that. Okay. So because this time I'm starting in grams, then I'm gonna have to convert to moles before I can do this calculation. So if this is my acetic acid here, and I'm using my periodic table from my exam handouts, oh, I can calculate a molecular weight for the acetic acid. So I have 2 times 12.011, which is the mass for the carbon on this. I can get it to scroll over. So carbon right there, 12.011 plus 4 times the hydrogen, which is 1.008. Where am I? There. And then I need to add the 2 times the 15.999 for the oxygen. So that's 60.052. And again, that relationship, I would have CH3COOH plus NH3, giving me NH4CH3COO. That's what happens when those two combine. That's the salt that I get out of that. So it's a 1-to-1 relationship between the two of them. So, and there's 1 mole of NH. And this one is the wrong one. So 1 mole of CH3COOH from that balanced equation to 1 mole of the NH3. And then if I have a 0.045 moles of NH3 in 1 liter, and of course, convert that to milliliters if that's what I want to do. So whether or not you do that conversion is entirely up to you. So I can do all of that happy math. 3.954 divided by the molecular weight that I calculated, divided by the 0.045, and then multiply that by 1,000 to get that volume in milliliters. And that's how many milliliters I would need to be able to do this using that particular solution. Okay. And again, this is all to remind you that this is the kind of calculations that we did last term to determine how much of each thing we would need or what kind of concentrations we were looking at. We went through all of that. Now, in your exam handouts, just in case you don't remember, there is something to help you. So if you come down here, I guess here. So this flowchart is supposed to help you remember all of the calculations that you would need to do to find those things. So again, if I'm in grams of A and I need to get to moles of A, I need to use the molecular weight. So to do that, whether I multiply or divide depends on which direction that I'm going. So all of this is a flowchart that's built out to tell you what pieces you need in between those things to get there. Okay, so it's just to help you remember. All right. So any questions about some of the stoichiometry calculations we've done? So let's calculate the molarity of an acetic acid solution if 34.57 milliliters of this solution are needed to neutralize 25.19 milliliters of 0.1025 molar sodium hydroxide. Okay, so that's what I'm talking about. First thing I want to do is to write myself a reaction. So acetic acid, I get CH3COOH, and that is on my list of stuff. So, just if I can't remember what that is, if I come down and look at my acids and bases, I know that here there's acetic acid and it tells me what the formula is. So there are some hints and things about what the formulas are, just in case you don't remember them. And it's okay, you don't need to know them all. So acetic acid plus NaOH will give me an NaCH3COO plus H2O. So I take the OH here, the H there, make a water, and then I'm left with sodium acetate. So the rest of this acid and that's sodium. So that's my relationship. It's a 1-to-1 relationship between the two of them. I have 34.57 milliliters of the acetic acid. And I am titrating 25.19 milliliters of the NaOH that happens to be 0.1025 mole. Okay, so that's the information I was given. That's how I put that with my equation to keep track of it. I always start with the thing I know the most about, which is the NaOH. So I have molarity and volume I can convert to moles. So I take that volume, 25.19 milliliters, convert that from milliliters to liters, multiply that times the molarity, 0.1025 moles of NaOH for 1 liter. That cancels the milliliters and the liters and leaves me in moles of NaOH. I know that there's 1 mole of NaOH for 1 mole of CH3COOH, which would then mean that I have the molarity of that, or the number of moles of the CH3COOH. And if I want that molarity, I need to get to moles per liter. So if I'm in moles, I can divide by the volume, 34.57 milliliters, and then convert from milliliters to liters. And that would give me a molarity for CH3COOH. So, doing all of my happy math, 25.19. And yes, I actually go through the 1000s, even though I've divided by 1000 here and I've multiplied by 1000 there. My head explodes if I don't do it. It's just one of those things. 0.0. Oh, sorry. 0.1025. Divide that by the 34.57 and do the other unit conversion. And that gives me a molarity for this of 0.0. And looking at the number of sig figs I have, all of the numbers that I was given, the volume here, this volume here, and this, all 3 of those have 4 sig figs. So I'm going to want to report this as 0.07469 molar. Okay. Cool. Now, how do you guys feel about these calculations? Do you want to continue with reviewing a couple more of these? Because these are all just the kind of thing that we've done before. So do you want to continue that? Do you want to take a look at any of these? Like maybe the one with the sulfuric acid?
Yeah, let's do that one if that's okay.
Yes. So, and I will post this one. In a titration, 25 milliliter sample of 0.129 molar sodium hydroxide was neutralized by 32.72 milliliters of sulfuric acid. What is the molarity of the sulfuric acid? Okay, so I take sodium hydroxide, I react that with sulfuric acid, which is H2SO4. When I do that reaction, I end up with Na2SO4 because SO4 is a 2- ion, so I need two NAs to balance it. And I end up with two H2Os, which means I need two of those to make that work, because if I don't have two NAs, I can't balance that correctly. So this is a 2-to-1 relationship, hence why I put it. Because again, everything that we've done so far has been this 1-to-1 relationship here. And so that M1V1 equals M2V2 would in theory work for you. This is not a case where that will happen. Right? I have a 25 milliliter sample of 0.129 molar, and this is 32.72 milliliters. I want to know what the molarity of this is. So start with what I know the most about. This guy right here, 25.00 milliliters. I will convert that to liters. I multiply by the concentration to 0.129 moles of NaOH in 1 liter. I know that there are 2 moles of NaOH required to react with 1 mole of H2SO4. And so this is where that stoichiometry comes into effect. That gives me 2 moles of H2SO4, and I have to divide by the volume in order to get to molarity. So that is my full calculation that I need to do. I will come over here. I'll take that 25. I'll divide that by 1,000. I will multiply that by the 0.129. I will divide that by 2 because of the stoichiometry. I'll divide by the 32.72 milliliters, and then I will multiply by that conversion factor again. And that gives me the following answer. And again, I have 3 sig figs here. This number, this volume has 4 sig figs. This has 4 sig figs. So my answer should be reported in 3 significant digits. So I would have 0.0493 molar H2SO4. So does that make sense? And again, I can do that at any point. I could make it so that I need, so that it's an H2SO4. I could have 2 OHs on the base that I'm working with. So we have to make sure that we're watching out for that, because if we don't take that stoichiometry into account, our numbers will be off. And you can almost guarantee you will see this, just to make sure that you do. And this will be untested. So questions about that? And one of the things that I hope that you've noticed as we've gone through this is, regardless of whether it was a strong acid or a strong base, as we're doing the titration, when we have those weak acids, they completely react with that strong base that we've added to it, as long as there is enough. Okay, so we can get to an equivalence point without much of an issue. The issues start to come in once we're at that equivalence point. What happens with that pH? So if we're looking at an acetic acid reaction, we've gotten to an equivalence point where this is what I have. Remember that that is an ionic compound. So that CH3COO minus is in solution. It can react with an H2O to give me back that CH3COOH and an OH minus. And so what that means is that my pH for that equivalence point will be above 7. Okay, so that equivalence point will not be at 7. And we can look at the concentration of the species that we had to determine what that pH will actually be. So based on things that we've done previously, so if I've converted all of this here, I can then set up a rice table to figure out how much of that is going to react backwards using the Ka to be able to determine what that pH is. Okay, so that's one thing. One of the other things is that if we don't have the right amount to get to the equivalence point, then we're going to have to determine how much of what is left over to determine what that pH is. And so that will just, depending on what we're talking about, we're either before the equivalence point, and so we need to look at how much acid we have at that point, or after the equivalence point, and we've added more base than we had if we're assuming we did an acid-base titration. And then it would be determined by the excess base. So all of those situations can and will apply to calculations you may get asked about. One of the things you may see on the second test is we will talk to you about, okay, I am doing this titration. At this point, what is the pH? At this point, what is the pH? At this point, what is the pH? And you'll probably get asked about what is the pH before the equivalence point, the pH at the equivalence point, and then the pH beyond the equivalence point. So that's 3 separate calculations. Does that make sense?
No, but it will.
Okay. All right. Then we will continue and we will talk about it. I want to talk about a couple of things before we do that part. So just things to remind you. So indicators are weak acids that have a different color in their base and their conjugate acid form, or their acid and their conjugate base form. So they look different depending on which form they're in. And that change gives us a different color. So that color change is what we're actually detecting after we've done whatever titration we were interested in. So if we're using a visual indicator, we finish whatever titration we're interested in, and then we start to titrate that weak acid or weak base, which then goes through the color change, which we detect. So our equivalence point where we have the number of moles of base is equal to the number of moles of acid for that thing that we're interested in is always before my end point, which is where we titrate the indicator. So there's a secondary acid that has a lower Ka that we're adding into this thing that we then titrate after that fact. So there's always a gap between the two. That's called our titration error. Sorry, brain fart. I couldn't remember. So titration error, the difference between those two things. And we have to make sure that our choice of indicator is actually after whatever we're trying to find. Because if it's not after that, then we can't be sure that the titration that we're interested in looking at has actually finished before we see the change in color. Okay? So while we understand that there is an error and we can correct for that error, it has to be done that way. Otherwise, we don't know that we know what we're looking at. Okay, so that is important to understand. The choice of indicator depends on where the Ka for your acid is, because that will determine the pH at the equivalence point. So we have to make sure that the Ka is smaller for the weak acid that we're trying to use as an indicator than it is for the acid that we're trying to titrate. Okay? And the same is true on the base side. So the pKb has to be smaller than the than the Kb for the acid or the base that we're trying to titrate if we were going the other direction. Okay? And of course, one of the other things that we know is that it's really important that we choose something that changes in the right space. So if we're looking at where phenolphthalein changes, that changes right about here. But if we're looking at an equivalence point that's way down here, that's a really big gap. Okay, so we want to make sure that that gap is as small as it can possibly be to minimize the titration. Okay, now obviously there are not an infinite number of indicators that we can use. There are only so many things that change color between their acid and base forms. So that's one of the reasons that we don't always do this with a visual indicator. So sometimes we'll do it with a pH meter, sometimes we'll do it with other types of mechanisms for determining this. Okay? So questions about that? Okay. So some things that I think that you should be able to do once you've worked through all of this stuff. You should be able to look at a titration diagram and tell me what kind of species was titrated based on where the equivalence point is. So was it a weak acid being titrated with a strong base? Was it a strong acid being titrated with a strong base? Or was it a weak acid and a weak base? Okay. So, and although you really won't be looking at a weak acid and a weak base, or was it a weak base with a strong acid? So based on equivalence point, you should be able to tell me that. Okay. You should be able to predict where the pH is at equivalence point for any of these titrations that you might get asked about. So if I asked you, hey, for the reaction between HCl and NaOH, where would you expect the equivalence point to be? Because it's a strong acid with a strong base, I would expect that equivalence point to be at pH 7. Because it's a strong acid and a strong base. If we were to look at something like a weak acid with a strong base, that pH is above 7. Because again, once we've generated that anion, it can react with the water and it raises the pH. Okay? If we were looking at a weak base with a strong acid, that pH is less than 7. So again, we look at a weak base, something like NH3, we react that with HCl. That gives us NH4Cl as the salt. That salt completely dissociates, gives us NH4 plus, which can react with H2O to give me NH3 again and NH3O plus, which again lowers my pH. Okay, so that's the kind of thing that we're talking is based on the reaction. You should be able to write that reaction, look at the products that are made, and then determine what kind of pH you would see from those products. And that uses that table that we have. So this one right here. So you should be able to predict that. And again, the things we would be talking about: strong acid, strong base, weak acid, strong base, or weak base, strong acid. We won't consider anything else. Right? You should be able to look at a titration curve and tell me if it's a polyprotic acid. So remember we talked about H2SO4 having a curve that looks something like this. If we're talking about pH on this axis and the volume that we've added, it comes up like this, and then it comes up again. And the fact that there are 2 peaks tells me that there are 2 acidic protons on that particular species. So you should be able to tell from the number of peaks that there are how many acidic protons there are on that species. And I know it's an acid because I started with a low pH. So, okay. And I won't ask you about the base side of this. I just don't. I just don't. So, you should be able to use this table to predict what the pH of a particular salt will be. So based on whatever that salt is, you should be able to tell me if the pH is 7, above 7, or below 7. Describe an endpoint and an equivalence point. You do need to know the difference between those two. And describe the action of an indicator. Okay, so what is the indicator? What happens to it? So you should now be able to talk about the fact that you have titrated a weak acid and it has gone from its acid form to its conjugate base form to change that color. So that's something else. A couple of other things that we talked about early in this particular lecture, and let me see if that's on the next slide. No, okay. So just a couple of other things. Henderson-Hasselbalch. So pH equals pKa plus the log of the concentration of base form over the concentration of the acid form. So when you're in the beginning part of that weak acid titration, as you start to go through this, so again, titration curve here, we start as a weak acid, we come up and we go through this sort of weird looking phase right here, then you go through equivalence point and up like this, just like we always do. This region right here is a buffer region. And so we can use the Henderson-Hasselbalch equation to determine what the pH is based on the fact that we have both conjugate acid or acid and its conjugate base. So
Okay, so do you only use this? I can't even pronounce this two guys' name, but do you only use that if there is a like an acid and the base present? That's the only time.
yes, so it's only
Okay.
used in buffer situations.
Okay.
If you don't have a buffer situation, i.e., there's not the acid and its conjugate base, or the base and its conjugate acid, then we would just use a Rice table and Ka.
Okay. Or KB, I guess. Okay. Yeah. Okay.
Yes, or KB. That is correct. Yes. And again, it is never wrong to always use the ice table. You can do that. There is no reason you have to use Henderson-Hasselbalch, but it is a nice shortcut for that. So I will not take points out if you don't use it in a buffer region.
Okay.
I may ask you if it's a buffer, and if you tell me it's not, then that'll be a problem, but that's a slightly different conversation. So okay. So again, places that I would expect you to be able to do calculations before before the equivalence point in that buffer region, I would expect that. So that would be based on how much of that reaction has happened. So how much base have I added? Therefore, how much acid have I converted to the base? So then I have the concentration of the conjugate base, concentration of the conjugate acid. Therefore, I can use Henderson-Hasselbalch to determine the pH. Okay, so that's that first portion. At the equivalence point, so based on what you have at the equivalence point, you should be able to determine what the pH is. And then after you've added too much base to this up in this region, then you should be able to tell me what the pH is based on how much of that you've added. So questions. And we have practiced all of those parts, how to calculate those things, all of them at some point.
I do have a question. So,
Yes.
like as far as the like finding the pH at equivalence points, like would you give us like the molarity of like an acid or like a base, or like do we have to like how is the problem set up? I'm like
So
trying to like
typically what you would be told is that I have this particular acid, like
okay.
benzoic acid, at 0.25 molar. So give me 2 seconds. Let me flip over here. So we might talk about benzoic acid, 0.25 molar, being titrated with 0.17 molar NaOH. And the way that you would see this, and we typically have like a 50 milliliter sample, just whatever. There's some volume of that acid that you're titrating. And I could say to you, after we add 10 mils base added, or I might say NaOH, What's pH? pH at equivalence point. What's the pH after 70 milliliters in AOH added? That's the kind of question I would expect.
Okay.
And again, I would be looking at how much acid did I have? How many moles of acid did I start with? How many moles of base have I added at each point? Right? Because I would have to calculate it for each point that I'm looking at to figure out what exactly is in that beaker. And then once I know what's in the beaker, I should know how to solve for the pH.
Hmm.
Do you want to see that?
Um, please, that would be amazing. If you got time.
Yeah, we can do that. So, I mean, if we're looking at this point where we've added 10 milliliters of that base, I know that initially, and I'm gonna have to come over here and give myself another piece of paper. So I had 50 milliliters, 0.25. I have 0.17 molar NaOH. I asked about 10 milliliters equivalents and 7. So those were the 3 points I asked about. So I'm going to take a look at the first one. And the first thing I'm going to do is ask myself, how many moles of acid do I have to begin with? So I usually set this up as a form of rice table. So my benzoic acid, at this point, I'm like, I don't know what that looks like, but let me go find it. So I come down here and I see that benzoic acid is C6H5COOH. I am reacting that with NaOH. That will then give me an NaC6H5COO and an H2O. So all I did was take one of these protons off and put that with the OH over here to make the H2O, and then I have this other thing that I'm left with. Okay, because that's the salt that I make. So that's the reaction that I'm looking at. When I have my initial conditions for this, I only have this stuff that I start with. And so I want to look at this in terms of moles because I know I'm doing reactions between the two of them. So I'm concerned about that. So, and I usually will tell you this is in, let's go this way, 750 milliliters is my total volume when I start. So I know that when I start, I am looking at, oh no, I have 50 milliliters when I start. Hold on. Let me get rid of that. Because I started with 50, so I've got an initial volume anyway, so never mind. So I have 50 milliliters that I start with, right? And I multiply that by the 0.25 moles of benzoic acid per liter. And that will tell me how many moles I start with, correct? So I have 0.0125 moles of the benzoic acid that I start with. And at the very beginning, I have no NaOH that's been added to that. So this is my initial table for this. Now, I have this 0.17 molar NaOH. And when I add the 10 mils, so my change for this, 10 milliliters times the 0.17 moles of NaOH. So that's how many moles of OH that I've added. And so in this change, I have the 0.017 moles here. And of course, these are all moles. I'm not going to bother to write that, but we're talking in moles for this. So what happens when that gets added is that I take this 0.0125 minus the 0.0017. This all gets used up by the reaction with this. So this is minus 0.0017. And of course, that means that I've generated 0.0017 moles of the base because I've converted that. So I know that that's what's happened when I do this process. Okay. So if I take those two values, this is how many moles of the acid I have left, 0.08108. And then this is going to be 0 at the equivalence for moles, and then this is going to be 0.0017. Okay, so that's how many moles of each of those things I have at that point. Okay, my total volume at that point, because I started with 50 and I added 10 to it, is 60 milliliters, right? So if I were to look at what is the pH, because I know I have acid and base, I'm going to use pH equals pKa plus the log of the base, which is the NaC6H5COO, over the acid, which is the C6H5COOH. Okay. Now, can I look up the Ka for benzoic acid? Of course I can, because of course it's in here. So it's right there, 6.25 times 10 to the minus fifth is the value of Ka. So pH is equal to the negative log of the 6.25 times 10 to the minus fifth, plus the log of the concentration of this species over the concentration of this species. And of course, that concentration is 0.0017 divided by 60 milliliters, which I have to convert to liters, right? So if I take my 60 milliliters, I divide that by 1,000 to get the volume in liters. I can now divide both of those, this, by that volume. And that tells me that the concentration of the base form is
Where did you
0.
get the 60 liters from? Or 60 milliliters?
It's 60 because
She
I had
added
50
10
when I
more.
started and I added 10
Okay,
to
so
it.
we're calculating for the 10 milliliters. Okay, sorry.
Yeah, no, that's fine. Totally fine. It's the total volume at that point. So that's where I get this number that I put in for the base. And then I can calculate the one for the acid, which is this guy right here, divided by that volume as well. And so that's the expression that I would have to solve to get the pH for that. Okay. And so if I do that on my calculator, I can take the negative log of 6.25 second e to the negative fifth plus the log of this number right here divided by that number right there. And that gives me that my pH at that point is equal to 3.40, which technically I would report as 3.4 because my Ka was 3 sig figs, so it should be 2 sig figs for the pH. So that's how I would get that one. Does that make sense? When I talk about my equivalence point, I have to think about what is the volume that it takes to get to that equivalence point, right? So if I'm asking about my equivalence point, and I know that I have this many moles to start with for my acid, then I have to start with that number. So the 0.0125 moles of, and I'm just going to call it BA because I don't feel like writing the whole thing out. So that's how many moles of BA that I need. That means I need to divide by the molarity of that NaOH, right? So the 0.17 molar NaOH. So 0.17 moles of NaOH per liter, because I know it's a one-to-one relationship between the two, right? So, I mean, technically speaking, 1 mole of NaOH reacts with 1 mole of benzoic acid. So that cancels with that and cancels with that. And that would then give me the volume in liters that I would need to add for this. You know, because I don't like to work in liters, I like to work in milliliters. I would do that. So that would tell me the volume of the NaOH that I needed to add to get to the equivalence point. Okay. So if I do that, 0.0125 divided by the 0.17, multiply that by 1,000, and that tells me that in order to get to that molarity, then I would need to, or to that equivalence point, I would need to add 73.53 milliliters of the NaOH to get to the equivalence, right? Because that would give me equal molar of the benzoic acid and the NaOH. Okay. So if that's the case, and I started with 50 milliliters, then the total volume at that point is 123. Okay, so that's one part of that I need to know. The other thing I have to think about is what exists in my beaker at the equivalence. So if I look at this initial table that I set up, I come back up here and I look at this, I know that at the equivalence point, I will have added enough NaOH to convert all of this to the basic form, correct? So I will have none of the acid left, and I'll only have the basic form. Now, if that's true, then that means that I will have 0.0125 moles of the C6H5COO minus in solution, right? And if that's the case, then what I can look at is the fact that we took the C6H5COOH. We have converted that to and so in this particular case, we are looking at what is the situation when I have 0.0125 moles of this and none of this. So that's what I'm looking at in terms of my K, right? Is how do I solve for that? And so because of the way that this works, because this is actually asking the basic form, one of the ways that I can do that is I can reverse this equation because it makes me way more comfortable to do it. And say that C6H5COO minus will react with H2O to give me that C6H5COOH plus OH minus, right? That's the back reaction that we get at the equivalence point. And that is set up because of the fact that I have 0.0125 moles of this. That I don't care about because it's liquid. What I'm solving for is what is the concentration of the OH to determine the pH. And so I can set that up in terms of the Kb for that reaction. And I can find the Kb by taking 1 times 10 to the minus 14th divided by the 6.25 times 10 to the minus 5th. Which is 1.6 times 10 to the minus 10th. And so if this is my initial condition, every time I take one of these and turn it into one of these, technically those are 0 to start with, then at equilibrium, I'm looking at 0.0125 moles minus X. This is X, and this is X. Right. So, and again, because that's not in a 1 liter solution, you need to put the molarity in there. That number of moles that exists here is going to have to be divided by that 123.53 milliliters. Which means that concentration right there. And so the approximation that I can work with. How many sig pigs are on? 3. Okay, times 10 to the minus 4th. And so I would put that into KB, which is equal to x squared over at 1.01 times 10 to the minus 4th. And so I can multiply KB, that 1.6 times 10 to the minus 10th times 1.01 times 10 to the minus 4th is equal to x squared. So I can take this number, multiply it by this lovely number right here, and then take the square root of both sides. Which means that my x value, which is equal to the OH minus, is equal to 1.27 times 10 to the minus 7. And so I can have my POH is equal to the negative log of that. Yeah. Forgot the negative, so it should actually be a positive 6.89 because I forgot the log right there. So and that means my pH minus. Technically it's 14 plus because I didn't change the sign. That's beside the point. So 7.10. So that's my pH at the equivalence based on the amount of that material that is able to dissociate. And then if we look at past the equivalence point, I know that it takes, oh, actually we never got past the equivalence point because if we wanted to look at 70 milliliters, that's before we get to the equivalence point. So bad choice. But if we were looking at that point where we had 70 milliliters, we'd go through the exact same set of calculations that we did right here to figure out how much of that base we had added and therefore how much of that material there was. I thought that that would be past the equivalence point, but that's because I didn't do the math first. So, and if it were past the equivalence point, then we would just be looking at how much additional OH have we added, because that additional OH would determine what the pH is. So the excess of the OH minus would determine the pH. Does that make sense? Okay. Well, the next couple of slides that I have in here were actually set to be, oh, actually this is from the one that we do in the actual physical experiment. So this is not about the weak acid that you guys do. So don't worry about that. And the rest was meant to be reviewed. So it's all old stuff. So questions about what we talked about in terms of titration? Now, given that the test has cut off already, and we're not covering the majority of this for the actual test, I feel like we have gone through enough stuff past what's going to be on the test for you guys to be pulling things together. And that's typically why I go over stuff that's past the test before we go to the test. So do you want to start the next lecture, or do you want to go get ready to take your test?
Well, I mean, I would rather get ready for the test, honestly. I feel like there's a lot of stuff here. I feel like especially with the
There,
homework for titrations was like very difficult. I really couldn't get through, like, I mean, it really took forever to get through everything. Because like I'm really struggling when to
because it
use
was just
the
like what we just did.
no, see the thing is like it doesn't make a lot of sense, you know? Like, I don't know. I feel like I would do a problem and then I feel pretty good about it and I put it in calculator and I get the wrong answer and I'm like what am I doing wrong, you know? So um I think it's like, I guess, like trying to figure out like what's left over, what's to use, like when to use that formula, when not to use it, like, you know, I don't know. With the
Well, so
buffer.
do you want do you want to talk about any of that?
Yeah, I mean, if you want to, for like,
That's up to you. This is your class time. You tell me what you want to talk about.
okay, yeah, if you could, can we like do like few of these problems from like the homework kind of titration, if that's possible? Like
So which one?
there was like a one when it was, I think the formula was, let me pull it up actually. So Alec let me out.
So we are talking about Alex.
Yeah, I mean, it was just the homework on it. I don't know. The last one, it was like 22 questions, and it felt like they were never gonna end. Honestly,
I can understand that. I can understand that.
I think I can still get into the, yeah, because I can take this, right?
Yes.
I think.
Yeah, you should still be able to get into it, and you should be able to share your screen, so that way we can look at what you're looking at. Because mine, I mean, there's a random number generator, so I don't always get the exact same question.
Oh,
You
hold on,
guys do.
I can do that. Oh, hold on.
You should be able to.
I think I need to like log in into the WebEx off of on
There
my
should be a
computer.
line down towards the bottom that says share.
So again, I
You said that the
yeah.
test is not. You said that you're opening it another day till Tuesday night, right?
Well, I am going to open it until Tuesday night. That is correct. I will get it posted as soon as I'm finished with it today. So
Okay, perfect. And then there's no like review on Alex, right? Is there any like?
there was, and I posted it to D2L.
Oh,
So the printout of it is on
Thank you.
D2L. Yes.
Thank you so much.
Yes.
Mm. So do I join it from the browser, or oh, no, can I just use it from the, no?
You should be able to do it for anywhere you're in.
Okay. Well, the thing is, like, I'm on my phone on this thing, so I can have the lecture open, so I can kind of like see what's up. But hold on, join the meeting. Okay, so share. Sorry. 1 second.
You'll get echoing as long as you've got both of them open, so you should close one of them.
Yeah, I'm trying to figure out how to like connect my AirPods here, because my wife and I were sharing the room, so I don't want her. Oh, it's just the two of us here anyway, so perfect. There. What am I have no idea how to do this. Oh, here we go. All right, perfect. Okay, so
Okay.
you can see the screen.
I can see your screen, yes.
Okay, perfect. So this is yeah, like, okay, like something like this, for instance. I feel like we just did this, and I think it's probably going to be a little. Can you hear me? Probably not.
Yes. Yes. I'm reading. I'm reading and listening.
Well, I can't hear you. I can hear me now.
Yeah.
No.
Okay. Yes, I can hear you. So.
Okay.
Okay. So
Hear me
what's
now?
up? Yes. Can you hear me?
Okay. I think.
Can you hear me?
Yeah. One second. How do you connect the AirPods to this thing? Oh my god. Oh, here you go. All right. Can you hear me now?
Yes. Can you hear me?
Okay. Perfect. Yeah. Okay. So I feel like okay. So I think my major problem is the thing is like that I can't really figure out how to use the or how to write the formula properly. You know, like because like I feel like there's like that spectator ions that you don't really count, and then there's like water that you don't really count. So you're really kind of like looking at, like for instance, if you have like a formula HClO plus KOH, how would you write that formula out?
So HClO plus KOH?
Yeah.
And are we talking
Would you write down
HCl?
like a KClO plus H2O, or would you write it down as a ClO like a minus as like a anion, and then like a water, and then a cation, which is a spectator there anyways? Like would it matter?
Well, so I mean, are we talking about HClO4?
Oh yeah, it could have been HClO4. See, like
Okay. So if I'm looking at HClO4, I'm going to react that with an NaOH. I know that's an acid-base reaction, right? And so I end up with an H2O and whatever's left over.
Right.
So NaClO4. Because ClO4 is a -1 ion, Na is a +1 ion. So they go together to make a salt. Whenever we do an acid-base reaction, unless it's with ammonia, we always end up with water and salt. And it's some kind, and what we mean by salt is cation and anion.
Okay.
So it's always the, if we're talking about NaOH, then it's always the Na. And if we're talking about H with some anion on it, then it's the A-. It's whatever's left after we take the H+ off.
Okay.
So, I mean, this one that you're looking at right here with methylamine, you got CH3, NH2. You would react that with HNO3. And when you do that, the H goes over to the CH3's NH, and it becomes NH3 plus. And then the other thing you're left with is the NO3 minus, which, because it's a positive and a negative, you can put together as CH3, NH3, NO3.
Okay.
So because you reacted with something along the lines of ammonia or methylamine, you end up with a cation and an anion stuck together. So instead of making water, because you don't make water when you have like an NH3 type compound, then they just become a cation and an anion.
Okay. There was one that, like, if you can see my nose, it's like I would do a calculation and then I'm like, okay, I got it all wrong, I think okay, this is the equation. I think I'm trying to find what number it was there. C3H7NH2 plus HClO4. That was the reaction.
So HClO4 plus
C3 H7 and H2.
C3H7 and H2. Okay.
So basically what I did, because it gave me the molarity of the C3, H7 and H2, which was 0.0660. And then it was the volume of that was 0.01791. And then it also gave me the molarity for the HClO4, which was 0.1, I'm so sorry, 0.5100. And then the volume on this one was 0.0024 with a pKb 3.46. So the way I went
Let
about
me
it.
verify.
Go ahead.
We have a 0.5100 molar HClO4 and it's 0.0024 liters or milliliters.
Liters.
Okay.
Well,
And then
because
we
there were
have-
milliliters and I transfer them over to liters. Yeah.
Okay. And then we have the 0.0660 molar CH3 or C3H7 NH2.
Right. And then
And
the volume of that one was 0.1791. So it was 17.91 milliliters. Oh, sorry. What was it?
17.91. Well, if it's 17.91 milliliters.
No. So it was whatever it was in milliliters. No. Sorry, I lost my AirPod again. Sorry. Okay. Just this one thing. Trying to find this. This is like the 16, 17. No. 20.
0.0179 liters.
Are those different questions or the same ones?
That's what?
If you were to take it the second time, is that going to be the same questions or no?
I mean, in theory, yes, it would give you the same questions the second time.
Yeah. Okay. So 0.171. Okay. No, something's wrong. Something's weird.
But again, if you went all the way through it and didn't answer it correctly, then when it comes back and gives you a new question, that'll be a different question.
That's true. Well, I got. Anyways, okay, so let's just say like we're working with this kind of numbers. Can we like hypothetically could? Okay, so basically what I did, I found the moles first of the C3, H7, and H2. Then I found the moles of the HClO4, right?
Right.
And then my limiting was the HClO4. So that means my acid was the limiting and the base was an excess. And I feel like that's where I struggle with, because like I feel like when I find acid in excess, it's a little bit easier to like calculate things. But when I hit like a base, I'm like struggling a little bit. So I started looking for the concentration of the OH, like, and then I found out, but then I didn't really need that, because I didn't really need the POH here, because I needed to find the moles, basically the moles of the C3H7 NH2 after all the HClO4 was used, right?
Yeah, the number of moles left over, correct.
Okay, and then you divide your the conjugate acid in this particular one, which is the HClO4, right? Which is the moles that I found, divided by the leftover of the moles from the C3H7NH2. Is that right? And then I would
Well, so
find,
go ahead.
and then that's how I would find, that would be like that log of the concentration of the BH over the concentration of B.
Well, so I mean, if it is true that your acid is your limiting reagent, you will have used all of that up. What will then happen is that all of the base that reacted with the acid becomes the conjugate acid of that base. So that fixes the concentration of the conjugate acid for that base.
Mm-hmm.
You then have the leftover amount of the base, right? And so and your Kb is equal to the concentration of the conjugate acid
Right.
times the OH minus over the concentration of the base.
So, and the concentration of the base in this particular equation would be the leftover, whatever
Correct.
wasn't not used? Okay.
Correct.
Okay.
Yes. And so there are two ways you can do this. You can put this into the Kb expression, not the pKb, but the Kb, and
Okay.
solve that. Or you can use the POH is equal to the pKb plus the concentration of the conjugate acid, conjugate acid over the concentration of the base, because that's the POH version of that, the Henderson-Hasselbalch equation.
Okay. Yeah, see,
So it
that's what I'm
depends
saying.
on
Like,
how you want to do it.
like what's the way to go about it if you were to do this problem?
Well, I mean, if it was me, I would do it through a rice table.
Okay.
And so what I would be looking at is, if I'm looking at it in terms of a rice table, I would be looking at the base going to the conjugate acid as my reaction, right?
Uh-huh.
And so the concentration of the base and the conjugate acid are fixed based on the reaction that I've done. So those equilibrium, the equilibrium row is fixed based on the reaction that I've done. So I have the amount of base that's still left over. I have the amount of conjugate acid that has been converted from the HClO. So that's the amount of the HClO that determines that, okay? Because it's a one-to-one relationship.
Uh-huh.
And so then I would have the concentration of the conjugate acid squared. Is that what I want to do? No. If I'm going to solve for that, so my Kb would be equal to the concentration of the conjugate acid times my X over the concentration of the base. And that's the Kb, so 10 to the negative pKb.
Mm-hmm.
And that's equal to the concentration of the conjugate acid divided by the concentration of the base. So if I multiply that over, I would then take 10 to the negative pKb times the concentration of the base that is left over divided by the concentration of the conjugate acid, which in this case you have as the concentration of the HClO,
Okay.
HClO4. And that would be equal to the OH minus.
Okay. Yes, I gotta.
Does that make sense?
I mean, it kind of does, but like it's. I don't know. There's just like so much, you know what I mean? Because like when they use the like the pH is the negative log of it. Like when you use this for like the formula, or like like for instance, if the buffer is like greater than the acid, there is no buffer anymore. If the acid is less than the base, there is a buffer region. So you got to figure that out. And then there is also I have like a bunch of this like little notes all over the place. You know, if it's a strong acid left over, then the pH is the negative log of the leftover acid over the total volume, right?
That's
Okay.
correct.
And then if you have like a weak base left over, then you just use the KB to solve for that.
That's correct. Because it's all dependent on what's in your beaker.
Okay. See, if both present, then you use that David Hasselhoff.
Correct. That's exactly why I call it that. Yes, that's exactly why. But yeah, I mean, that's exactly what it is. And I know that sounds ridiculous because I keep saying, what's in the beaker? What's in the beaker? What's in the beaker? But that's what matters because that's what's going to determine your pH. Because you've got to look at what contributes to that. Because once you've done some conversion of something to something else, you're now in a situation that will soon be calling a common ion situation. And so that means that your rice table is not as easy as it used to be.
Okay. Okay. One more question before I let you go.
Yes.
Oh my God, it was just on my mind. I don't know. If I think about it, I'll send you an email. I'm sorry. I
Okay.
totally just
No,
had
that's
that in my
perfectly
mind.
totally fine. I totally get it.
Okay, so yeah. So that Hasselhoff thing for the OH, that would just be the PKB plus the log of the concentration of acid over the concentration of base.
No, your PKB is the negative log of KB. Remember? So it's 10 to the negative KB is equal to KB.
Right. But I'm saying like if you're looking for the POH, would that be like the formula for that would be the PKB plus the log of the concentration of acid over the concentration of base? Because the pH formula is the pKa plus the log of the concentration of base over the concentration of acid.
As long as it's the conjugate acid over the base, yes. So it's not the
Oh, so it's
HClO4.
Conjugate. Okay, that makes sense.
Yeah.
See. Okay. So that's only applicable if they are conjugate, but if they're not, then you use the KB formula for that.
Well, I mean, either way, you're always looking at the concentration of the conjugate acid and the base, or the base or the conjugate base and the acid. Either way, it doesn't matter which one you're doing, because Ka and Kb are always written that way. It's never the acid that you're titrating with. It's always the species that's built, the conjugate that we have to look at.
Okay, that makes sense.
Yes.
All right. Thank you so much.
Awesome. If you run into anything else, let me know.
I probably will. Thank you. Yeah, I think I'm gonna start getting ready for it. And I don't know, like I did all the homework and then I mean it took me all day yesterday to finish it up. And like the beginning was kind of easy and then I just kind of like hit a snag. Maybe it was like late in the night and I couldn't really compute that in my mind, but all right.
Again, half of that we hadn't really talked about yet. So I'm not surprised you hit a snag with that one because we hadn't finished it yet. So
That is true. All right.
And it's not on the test. Not yet. So
Thank you so much. Are you running the bridge tomorrow?
no. Oh God, no. Hell no. I have to be at the Flower Town Festival.
We'll have fun. Enjoy some
Well,
of it.
thanks. All
Yes,
right.
ma'am.
I
Have a
will
good
see you
weekend.
later. Let me know if you need anything.
I will.
Okay.
Bye.
Thanks.